Welcome students, and in this activity we're going to have an introduction to qualitative analysis. Specifically, we're going to study what are called the group 1 ions. If you had your lab manual with you, this would correspond to experiment P14 in our class. Let's start out by remembering something. What happens if you mix solutions of sodium chloride and silver nitrate? You might remember this from a previous course, right? You get a precipitation reaction. And if we write it out, we see that there has been an exchange of ions. We call it a double replacement reaction. And one of the products is silver chloride, which is a solid, in other words, a precipitate. Now, in our previous courses, perhaps you are accustomed to treating this as though the compound, in this case silver chloride, is either soluble or it's insoluble. Kind of like an all or none type of thing. But actually, if we could observe the behavior of this mixture at the, let's say, the atomic scale, we would see that what's actually happening is an equilibrium between the undissolved solid and its ions, which would actually be dissolved. Now, this is, again, a reversible process. At equilibrium, it has an equilibrium constant, which, because we don't include the solids in the expression, and the solids are the only reactant, quote unquote, that we have here, what this ends up being is the product of the concentrations of silver times chloride ions. And because of that, we sometimes call this the KSP, or the solubility product. As you might expect, typically, the value of this equilibrium constant, KSP, is very, very small because most of the ions are actually in the insoluble compound, in the solid. As any other equilibrium constant, KSP is dependent on temperature, and for most compounds, K increases as the temperature increases. In other words, these compounds tend to be a little more soluble at higher temperatures. However, let's say that you had, instead of mixing sodium chloride with silver nitrate, you had mixed it with copper 2 nitrate. In this case, we don't get a reaction. The presumptive combination of copper 2 ions with chloride ions are as soluble as the copper 2 nitrate. So it tells us that there are differences in the solubilities of these different compounds. And so we introduce this methodology that we call qualitative analysis. The strategy is that given an aqueous solution of ionic compounds, we can use their different solubility properties to separate them. Qualitative analysis is the process of identifying which substances are present, but not necessarily their amounts. Gravimetric and volumetric analysis, which you may or may not have done earlier, but for example, titration is a volumetric method. All of these are quantitative processes. They're meant to find how much of a substance is present. Our initial focus is going to be on metal cations, that is, the cations formed by elements in the metals section of the periodic table. We're not going to study all of them, but what we're going to find out is that following this strategy of selectively precipitating some cations versus others, we can devise a strategy for the separation and identification of these cations. Now, based on the reactions that we use, we can separate them in groups. For example, if in our first step we add HCl to a solution containing, let's say, 25 of these cations, we're going to precipitate 3 of them in the form of chlorides, lead 2, mercury 1, and silver, and we call this the group 1. Now, what you would do in a regular sequential set of precipitations is you would then precipitate the next group of ions as an acidic sulfide group, and you can see the list there. This is group 2, and then you could make the solution basic and precipitate the next group of sulfides, which is group 3, and then you could precipitate the next group as carbonates, and this would be group 4. And there's a few ions, for example, sodium, potassium, that are not going to precipitate with hardly anything. So they're usually identified by different methods. Now, in our activity of this week, we're going to be focusing on group 1. These are the 3 cations that precipitate in the presence of hydrochloric acid. Group 1. Now, what I'm going to do is I'm going to discuss some general strategies and tactics involved in qualitative analysis. And then in a different video, you'll get a chance to go step by step carefully through the whole procedure. In qualitative analysis, we have 2 types of tests: separation and confirmation. For separation, we use a reaction to cause the precipitation of one component, or alternatively, we use a reaction to selectively dissolve one component from a precipitate. Then we physically separate the solid phase from the dissolved components. The purpose of this type of test is simply to separate the ions. We then do a confirmation test. We use a reaction that is specific for the separated component. Now, sometimes we can use one reaction to confirm more than one component, and actually we're going to be doing that in this separation and identification of group 1 ions. One of the techniques that we use is the formation of complex ions. We have seen this previously in our activity on finding the equilibrium constant of a reversible reaction. We saw how iron 3 ions and thiocyanate ions can react to form an equilibrium mixture where you have this complex ion with the iron thiocyanate, right? So the reason why metal cations can do this is they can form these complex ions because of their available unfilled d orbitals. We will discuss this more in detail at a later time in the semester. Now, we can also manipulate these complex ions in different ways. Let me give you an example. Let's look back at the equilibrium between the undissolved silver chloride and the dissolved and dissociated ions. It turns out that if you add ammonia to a solution that has silver ions in it, those two are capable of forming a complex ion that has a silver cation and 2 molecules of ammonia, retaining the positive charge. This process has a very high equilibrium constant. In other words, it is very favorable towards the right. It is positioned favoring the product, which is the complex ion. So let's apply the Le Chatelier principle. If you are forming this complex ion at a high rate, that means that according to Le Chatelier principle, you are pulling out the silver ions from the left side of the equation. You're pushing this towards the right. Silver ions are getting removed. That means that if you look at the equilibrium of solubility above, if the right side of that equation where the silver ions are they're getting removed. Let me use a highlighter to show you what I mean. If in this case the concentration of silver ions is going down because you are pulling them into this equilibrium, that means that the silver chloride is going to be displaced towards the right to compensate. In other words, you're going to end up dissolving more of the silver chloride. And I will discuss this more in detail in our explanation of the experiment. Now, remember, although the addition of ammonia essentially dissolves the silver chloride precipitate, ammonia itself is a base. So if you were to react this with an acid, you form the ammonium ion. But think again about the Le Chatelier principle. If I now add acid to this combination I have here, I am now causing the ammonia to be removed from the solution. If I remove ammonia from this solution here, from the second equilibrium, that means that that equilibrium is going to be displaced back towards the left. And that means you're going to increase, I'm going to do this in a different color here, you're going to end up increasing the concentration of silver ions, which is then going to cause this equilibrium on the top to get displaced back towards the insoluble silver chloride. And so as a result, the addition of acid reprecipitates the silver chloride. So this gives you a set of tools where you can precipitate silver ions as chlorides, then redissolve them, and then reprecipitate them again. And you'll see the place that each one of these steps takes in our scheme to identify by separating and confirming the presence of the silver ion. Now, some techniques. First of all, again, if you are just going to be doing this as a virtual activity, in other words, you're not going to be physically in the lab, it'll be good still to understand the techniques. For example, you're typically going to work with samples in small test tubes. Your samples are typically going to be about 1 milliliter in volume, and that's about 15 to 20 drops typically. You want to add the precipitating reagent drop-wise. In other words, you don't want to squirt it all in. You want to add it drop-wise, mixing in between using a small glass stir rod. The precipitation reaction can look in different ways. In other words, precipitation can make the mixture look cloudy, or it can look lumpy, or it can look kind of silky. So any one of those types of observations leads you to the conclusion that precipitation has happened. Now, in qualitative analysis, we are going to use a centrifuge, typically spinning our samples for about 2 minutes, which is why we want to use small test tubes, because typically the centrifuges that we use are set up to fit those size of test tubes. Now, before you do your centrifugation, you need to balance your reaction test tube either with other students' test tubes or with a test tube with water. And you're simply going to equalize the volume in the test tube visually. There's no need to measure them to the hundredths of a milliliter. None of that. You want to just visually balance them. Now, when you place the test tubes in the centrifuge, they also have to be balanced so that the weight will be evenly distributed. Here is a schematic of some of the ways. Let's say you have 2 test tubes. You can balance them simply on opposite sides of the rotor. If you have 3, you can balance them like in a triangle arrangement. If you have 4, you would put 2 and 2, each pair opposing each other. And of course, you can also have a full centrifuge. In a real lab, I encourage my students to cooperate and try to go into the centrifuge together with all their test tubes so we can maximize the use of time and you don't have students waiting for someone to finish their spin so they can do theirs. Now, once you have done the centrifugation, your mixture might look like this. You'll have a packed precipitate, which we sometimes call a pellet, and then you'll have the clear supernatant, sometimes abbreviated as supernate. And what you will do is you will decant the supernatant into another test tube. That means to very carefully pour it out, making sure you don't disturb the pellet, you don't drag any of the solid with you, which is why it's important to give it a good spin so that the pellet will pack very tightly. Now, you're not done yet. The supernatant that you have decanted might still have some of the stuff you wanted to precipitate, but either it didn't precipitate or it didn't make it into the pellet. So what you'll do is you'll add more precipitation reagent to the supernatant, and if you observe that there is some more precipitation, just recombine it with your pellet, mix it well, and respin it. Now you can decant this second supernatant into a clean test tube if necessary for further analysis. Now the pellet, once you have it and you've decanted the supernate, you will wash it. You do this by usually adding water, mixing it, and mixing it means you'll go in with a stir rod and really break up the pellet, get it really mixed with water, and respinning. The idea here is to make sure that anything that should not be in the pellet gets washed away. Now, this second supernatant, you don't need to keep it. You can just discard it. Of course, making sure we are aware of potential waste management issues, all right? Okay, the other technique that we use is heating. Now, in these types of experiments, we usually don't heat the samples directly, like we don't put them in a Bunsen burner. That's too drastic. What we do is we prepare a small beaker with water on a hot plate and we heat it until it boils. At that point, we want to adjust the heat to prevent excessive boiling and splashing of the water. Because the test tubes are very small, it would be very easy for them to either float or actually tip over inside the beaker. So you don't want to use a very big beaker. And then what you do is this kind of trick here where you support the test tube using a clothespin so that it stays submerged sufficiently in the water but with no risk of falling down. This technique can also be used when you're trying to chill the mixture in ice water. In ice water. You can also use the same technique with the clothespin. Another technique that we use is sometimes we need to adjust the pH. I mentioned earlier that sometimes the acidity of the reaction mixture can tip the reaction equilibria in one direction or the other. Now, there are two possibilities here. If the procedure simply requires you to make the solution acidic or basic, so just generally acidic or generally basic, what you do is you're going to add the acid or base dropwise. In other words, don't dump a bunch of liquid in there. Typically, the acid and base reagents that we have in the lab are stock solutions that are typically 1 molar in concentration. If the ones that is provided is of higher molarity and you are asked to use 1 molar, you'll have to dilute the stock solution provided to make it 1 molar. This one you test with litmus paper. Of course, you should remember the litmus paper test that we've studied before. Remember, all we're asking here is to see if the solution is acid or base. That's all we need. We don't need an exact pH. Now, there are some procedures where you're required to adjust the solution to a specific pH. Now, in that case, what you're going to do is you're going to use pH paper, not litmus paper, pH paper. These are pieces of paper that are coated with different types of chemicals, and so they give you a color reaction that you can match against a, kind of like a little key that they give you here in the container, and you can more or less calculate the pH. Sometimes plus or minus 1 unit. Sometimes it can be more specific. There's pH papers that just cover the range, let's say pH 1 to pH 5. So you can get a pretty exact calculation there, okay? Importantly, never submerge the test paper, whether it's litmus or pH, into the solution. What you do is you slightly insert a glass rod into the solution and you basically dab the test paper with the glass rod, just in one little corner of the test paper. That way, you can do multiple tests on one strip of test paper. Mainly, it helps with the economy and it minimizes the amount of solid waste that we had to get rid of. Speaking of, let's talk about safety and waste disposal to close out this introduction. Remember, always wear goggles. And if you happen to spill any chemicals on your hands, just wash them immediately under the sink, not just briefly, but for a couple minutes. Make sure you dispose of chemical waste in the indicated waste containers. There will usually be a container for liquids and one for solids. Most of the time, the majority of your waste will be liquid, or it might be like heterogeneous mixtures, a little bit of precipitate in them. That's fine. You will dispose of them in the indicated waste container. Now, because most of your samples are small and you do repetitive washes and stuff, it might be better to set up a liquid waste disposal beaker in the fume hood in the area where you're working to collect the waste. So you collect the waste there, and that way, instead of making multiple trips to the main waste container, at the end of the session, you take your disposal beaker and you bring it over and you dump your waste into the container. Now, make sure you only dispose of primary liquid waste. Understand, this waste that we generate has to be processed by the proper agencies. And so we don't want to put in more waste there than we need. By the time that you have, for example, washed a pallet, there's very little, if any, chemicals left in that supernatant. So supernatant from washings, that is not primary waste. We can just flush that down the drain. Remember, if you spill any acid, let's say on your bench or on the fume hood, before you wipe the surface with a paper towel, first make sure that you neutralize it with baking soda. And when you finish, all your used test tubes and glass rods will go into indicated tray or container. Usually also in the cases later on where we use the dispenser or Pasteur pipettes, those will also go into those tray containers. So there's several things. We'll have like a little tray or a container where you put all this stuff, and our lab stockroom will take care of washing that and cleaning it later on. Very important. Before you return the hot plates to their storage place, make sure you've cooled them down. You don't want to put a hot plate in the storage area and then some other students coming in accidentally touching it and burning their hands. Okay, very important. Okay, I hope that is a thorough introduction. In the future, when we do other types of activities of this form, of this type, you may want to refer back to this video so you can review the basic techniques. Even though in each one of the labs you will do, we will take care of making sure that we've reviewed some of these, or we detail the ones that we haven't covered here or that we covered in a very general way. Now I encourage you to go to the next set of videos as described in your assignment box. Thank you.